So my talk is going to be using the nonlinear solver. How many watched Alex Candelo's talk yesterday? Raise hands. Okay, good number of hands. That's awesome, because I'm going to be pointing things out about his talk during my talk, okay? So we're going to take this from an example that came from some customer engagements with capacitated multi-vehicle routing problems. Just as a reminder, D-Wave has multiple types of hybrid solvers available in our cloud service. The one we're talking about is the nonlinear model solver. And the special part of that solver is that we can move beyond quadratic interactions. And like Alex said, we're able to kind of take constraints and build them into the model variables, which significantly reduces the model size. So we'll talk about that along the way. We also have some other hybrid solvers for different purposes. The constrained quadratic model solver, that looks very similar to what folks are used to in the OR space in terms of modeling something as an objective function and then adding constraints. The difference here is that we want to have a quadratic program, not a linear program for this model class. And then finally, our binary quadratic model solver looks very similar to problems that you would actually send to the chip, to the QPU chip. However, you can kind of extend the size a little bit larger. So these are the hybrid solvers that we have, and like I said, I'm going to talk about the nonlinear one. These different model classes have different characteristics and different sizes of problems based off of those characteristics. So for example, the nonlinear model solver, we have evidence of it solving up to 2 million variables in that model class. Whereas the constrained quadratic model solver, we're able to add 100,000 constraints in that model class. The binary the binary quadratic model solver, 1 million variables. So different flavors based off of the problem that you're looking at. Again, today, we are going to be talking mostly about the nonlinear model solver. So there's a massive amount of documentation about these two on our website. I encourage you to go check those out if you want to know more about these two. Okay, so where does this talk kind of come from, and what are we going to be speaking about? So D-Wave has, in our professional services team, we've been doing a lot of work on different classes of problems, and lots of them are modeled out in those demo booths in the hall. What we're going to talk about today are routing classes of problems. So this was some work that we did last year with Momentum Worldwide. It was a routing-based problem for actually a marketing campaign where they wanted to go from different cities and set up different sorts of resources. So we worked with them in our professional services team to build a model and do some benchmarking about the best way to kind of allocate those resources along the different routes. So the majority of what we're going to talk about today comes from real customer problems translated into a simple model that is open source and available for you all to play around with. We're also going to go through this in kind of a systematic framework that our professional services team uses when they start to look at building applications. And this is not necessarily like specific to D-Wave, but it's useful to kind of think about things in these steps, and that's how we're going to go through discussing what's going on in the solvers. So first step, problem discovery. We want to think about what it is that we're going to try and optimize. Why is this important? And I want to point out that second bullet point, because that really is the core of what we look for in good problems. Something that's going to be valuable to the business that we're contracting with. Because if it's not valuable to that business, likely they won't adapt it into production, and that's always our goal when we build these applications. Next, we'll talk about how we write down a problem description, the information that we look for, and we'll see it through an example, as well as the problem formulation. That's where we get to the good technical stuff. and then we'll see the code that's required to take the optimization problem formulation and actually send it to the nonlinear solver. And then finally, we're going to motivate the next steps. So we'll look at what it would mean to take this example and even push it further, customize it for the business problem that we may be interested in. So this is the problem we're going to tackle. We're going to tackle capacitated multi-vehicle routing, where we have a series of locations that are requiring some sort of resource and a central location where all of our trucks are going to kind of leave from. And what we want to do is we want to be able to optimize the distance being traveled by these trucks. So the question is, in terms of a business case, how do we satisfy demand without wasting money on fuel? So minimizing that distance. Currently, part of our discovery process would be to say, hey, how are you doing this right now? And so we'll imagine that these schedules are created manually. So every 2 to 3 weeks, we create a schedule. That takes a lot of time. It takes a lot of manpower to do this by hand, for example. Now, step one, now that we kind of understand a little bit about the situation, we'll do some problem discovery. So how do we do discovery for the nonlinear solver? We often look for specific characteristics in these problems to kind of pull out for our different professional services projects. And so I've listed them here. So characteristics of good candidate problems. First off, we want to make sure that we have decisions that influence each other. That's going to take advantage of the nonlinear portion of the solver, as well as, remember, Alex talked about that quadratic optimization. We really need to have variables that affect each other to take advantage of that. So this top one is very important. Moreover, we'll look for mostly discrete decisions or choices. That also gets back to the quantum optimization. We want to be able to have some confidence in that process. So we'll look for discrete decisions or choices. Too many possible answers to try. Our friends from SAS talked about that the other day as well. We want to look for a very large sort of problem landscape. Many rules that need to be satisfied. Okay, friends from SAS again talked about that as well, how we can use the nonlinear solver to take those constraints, reformulate the problem, reduce them, and get feasible solutions where other solvers may not be able to fit the bill. This last point gets back to the business case. We want to focus on problems where current solutions don't exist or don't perform well, because that helps with adoption. That helps us make the case later on that, hey, we worked on something important, and you should think about investing more. Okay. So with our professional services team, we've seen a few trends of where these good problem candidate classes come from. I'm not going to read all of the different examples on the slide. You're welcome to take a picture. It's going to be in the recording. But I do want to point out that every single one of these classes is represented in the demos outside. So for resource allocation, we're demoing our VM loading example, or load balancing example, that we actually use in our own production at D-Wave today. For production scheduling, we're demoing flow shop scheduling. For workforce scheduling, we have a retail assignment problem outside, so retail workforce assignment problem. And then for resource routing, we have this example that we're going to go through, the capacitated multi-vehicle routing problem. So if you haven't taken a look, go check those out. When we've identified a use case, then we start to go a little bit deeper. So we talk about the business case, then we look for a little bit more sort of like technical information in these problems. Things like, what sort of optimization are they looking for? Things like, do we have something that we can model as a permutation or a combination? Because that's really where the nonlinear solver starts to shine. Trends that we've noticed are we're looking for problems that are a little bit too complex for classical. That could mean we're not getting feasible solutions. It could mean we're not getting feasible solutions in the time limit that we care about. And then for additional details, like we said before, we want to take advantage of the nonlinearity. We want to make sure that we can use the matrix operations that are kind of embedded inside the solver itself. And it is also very helpful for us to kind of investigate a current classical formulation to kind of see where can we take that formulation and adapt it to the nonlinear solver. Okay. We also have some customer examples, and again, I'm not going to read through all of these, that take advantage of those different sorts of characteristics. So for optimization problems, we've worked with maximization, minimization, permutation. We have the flow shop scheduling, quadratic assignment, workforce scheduling, and then we also have combination problems for network partitioning and community detection. Let's get back to our example, though. And go through a bit of the problem discovery process. So when we go through problem discovery, we're really looking for set pieces of information. We want to think about what the problem goal is, state that out, what the proposal is, what are we trying to do with this solution, and then we want to think about, okay, well, what information do I need to know and how am I going to ask that? So for this problem, our goal is going to be to reduce fuel costs as well as the time it takes to build the schedules. Remember, we're in a situation where they're building schedules by hand and it's taking 2 to 3 weeks to get those started. We also want to make sure that we don't violate the requirements for the deliveries themselves. So our proposal is going to be to build a quantum optimization application. No surprise there, we're here at D-Wave where we do quantum optimization applications that provides a delivery schedule. Now, what questions do we need to ask? You notice I had a big chunk, the people paying attention, there was a big chunk there, and no surprise, there's a lot of questions that we have to ask, and this is just a small flavor of them. But we'll ask questions about the current solution, we'll ask questions about the business case. So for example here, how much could the company save on deliveries if the total distance traveled was reduced by 5%? That's a very important question when we go through the discovery process. What does this solution mean to you? What information about the delivery locations are currently available? What sort of information are we getting into this application so then we can build those schedules? Okay. Once we've gone through that process and we've answered all of those questions, then we'll go through and we'll build a problem description. So for this case, we'll take all of that information and we'll write down a goal. Goal is we want to create multiple vehicle routes to supply food, water, and other necessities to these locations, and that exactly models the demo that's outside. The challenges to meet this goal is to make sure that we're reducing the total distance and we don't overload the trucks. Okay, so we don't exceed the carrying capacity. Once we've written down that problem, then we can start thinking about what our input's going to be, what's our desired output, what should decision variables answer for us, what is the objective function going to correspond to, and what restrictions do we have to keep track of. So in this description, we'll write down in words those items. So we need delivery locations and requirements. We need to know the number of available trucks. We need to know their carrying capacity. We need to know where that depot is. So we have all the information to kind of build this problem. Our output is going to be a delivery order for each truck. So that's going to correspond to the schedule. And then the decision variables are going to tell us which truck should visit which location in which order. Our objective function, hopefully is not shocking, minimize total distance for all trucks. And then the restrictions are going to be make sure you don't exceed the carrying capacity for a truck, so you can't overload a truck. And then also, you want to make sure you meet the requirements of the delivery location at a high level. Okay, so this is the problem in words. the next step is to write down the problem in terms that the nonlinear solver will start to understand. So we'll start doing a problem formulation. Now this is a problem that we actually originally looked at first with the constrained quadratic model solver. So when we write down the objective and example constraints for an MIQP formulation of this problem, we have to do a couple of things, like make sure we satisfy that we are not like visiting places twice, or that we actually visit everywhere we're supposed to, okay? With the nonlinear solver, we can actually remove those because we'll include those constraints as implicit constraints in the variable that we choose. There's a question.
What if visiting a site twice actually gets a better result? Why overly constrain it if you only visit a site once?
Because in our situation, we have specific delivery requirements for each place. And so the assumption is if we have to deliver twice, then we're backtracking, we're wasting fuel. So at each location, we're gonna meet the delivery requirements every time we stop and then move forward. So there's no backtracking. Now remember that the nonlinear solver philosophy takes advantage of a couple of items. First off, we're using classical compute power, we're also using quantum compute power, and we're taking advantage of constraint programming. So we're going to use in the solver mixed integer linear programming. We're going to use quantum optimization, just like Alex talked about yesterday in his talk about the nonlinear solver. However, what we're really going to focus on here and take advantage of is the constraint programming portion. All of those constraints getting wrapped into an actual object that allows us to eliminate them from the model in the terms of like writing down this constraint equals this. Okay. So the nonlinear solver has a couple of characteristics, and Alex gave some previews of that yesterday as well. The general model itself you can think of as a directed acyclic graph, where at the bottom level, and don't worry, we'll see this all explained a little bit more in detail, but the bottom level holds the variables and the model constants, and then we kind of build up the mathematical operations to the top level of this graph. Then what we'll talk about today are different variable types. So we have set variables that encodes unordered subsets of a specified range. So for example, if you set y equals set 3, that's defining a variable where these are the possible return values. So you're getting the return values will be any sort of subset of 0, 1, 3, including the empty set. Then for list variables, we're looking at all possible permutations on a set range of values. So on the other side, for a list variable, if we set y equals list 3, then we get all possible permutations of those two values, 0, 2, 1. And that is what we're going to use to define how our trucks are going to travel from location to location. So we're going to start off simple, and then we're going to build complexity. So our goal problem is a multi-vehicle routing problem. We'll start with a single vehicle routing problem. So for a single vehicle routing problem, our variables are going to be what locations a single truck visits in which order. So we'll use a list variable to define that. And then the objective is going to be minimizing the distance between stops and a return to origin. So we're going to take the list variable and we're going to build a directed acyclic graph that incorporates those two distances. So we need the distances between one location and another location to be incorporated into the model. Okay, so this is what that graph structure looks like for an itinerary. What the itinerary means is we have an initial starting place, and we're going to go until we reach the end of our travels, okay? So define a couple of things. X is going to be our list variable. That's at the bottom of our graph. So here's our list variable X at the bottom. D is going to be all of the distances between all of the different locations we're going to consider. And then we'll talk about how things kind of move forward from there. The objective function written down of what we're actually trying to minimize is this. So we're minimizing the distance traveled between different locations all added together. Now, next, okay, we're going to get a little bit more technical. I know this is already looking a little scary, but I'm going to try and explain it using data flowing through this model. So an initial list could look like this. 4 locations, 0, 1, 2, 3. Distances between those locations could look like this. Okay, so here is a distance matrix where, for example, we have on the diagonal the distance from basically staying in the place where you are. There's no distance there. But if we move from location 0 to location 1, then we have 656 units of distance, assume feet. Okay, so we'll set those into the model. And then we have these indexing nodes. So this next step is an index where we're going to pull information out of the list. We're going to pull information out of this matrix here. So let me show you how that works. So first off, here, we're looking at this subset of our list for our initial index in the distance matrix, and then we're looking at this subset for the other side. What that looks like, what we're actually going to pull from the distance matrix is then this submatrix. That gets pulled out by our indexing node here, and the sum is going to add up everything on the diagonal. Okay, so we're going to add up everything on the diagonal, and that is going to be the current cost of the objective function for this arrangement of traveling through the locations. Now, what the nonlinear solver does is it looks at that structure and it uses classical and quantum optimization methods to change this ordering to make this as small as possible. So, for example, if I just switch those two interior values, so instead of 0, 1, 2, 3, 0, 2, 1, 3, that changes what gets pulled out of the distance matrix. That changes what's on the diagonal. That reduced my objective cost. Okay? So that would be a smart transition or move for this solver to make. Now, some of you may have noticed, oh, that's just the itinerary. What about like the distance traveling backwards? You have to go back to your start, your depot. What this model fully looks like for a single vehicle routing problem is actually this. The itinerary that we just went through is this direction, and then this here is the return to start. So this is our single vehicle routing problem in the graph structure. Okay, so we'll use that as our problem formulation. Okay, single vehicle routing problem formulation. What did we do? We looked at a simple version of the problem. We said instead of looking at multi-vehicle routing, I'm going to look at single vehicle routing. We tailored the formulation to the optimization model by choosing variable types, developing the model based off of the objective function, and then added additional constraints. Okay, the next step is going to be problem formulation. So here, we're going to include some pre-processing. We're going to look at what this looks like in D-Wave's SDK, and then we're going to use an API call to solve it, and we'll look at post-processing. We're still in the single vehicle routing space. What does this look like in a client architecture, though? So we saw some examples of this a little bit earlier on. What we're building is this right here. The piece of the client architecture structure that's going to actually build the optimization problem. Then we'll use an API call to send it to D-Wave system over here. using classical compute resources and quantum compute resources to solve that problem and then send it back to the client side. And the code to do that lives in our Ocean software development kit. So at the very bottom of our stack, we have our hard compute resources. What we've built on top of it, well, what Alex's team has built on top of it, and our other software development groups, are these ways to kind of connect to those resources. We call them typically samplers. So we'll use the nonlinear hybrid sampler to send a nonlinear model class, which uses this, I want to call this out specifically, a problem generator, to solve a multi-vehicle routing optimization problem. So high level up here, we have applications. This is how we send things to the compute resources. All right, so for the model setup, here's where we look at code. This will encode that model that we put together. First, we have some import statements. Here's our hard-coded distance matrix that we looked at before. Here we're setting up the model, instantiate the model class, add the constants. That's the very bottom row that we were looking at. Then we define the itinerary, and we define the return to origin. We add those together into our model. That's the objective function there. So here we've set up the single vehicle routing problem. After we set up the problem, we have to send it to D-Wave. So here, we're going to instantiate a sampler. That's going to make the connection to D-Wave's backend. This line is what sends that problem to D-Wave's backend and says, please optimize this model. Then we'll post-process some results. And so I ran this, and what I got out of it was optimal solution 2130 in that order, and there's my total distance. Okay. Now you might be saying to yourself, okay, this seems kind of familiar, like routing problems. You know, some of us are familiar in the quantum computing space. This seems like something I've seen before. That's because it is. This is a traveling salesperson problem, and our model generator class has this built in already. So you could write out the code that I just walked us through, or you are welcome to use the traveling salesperson model that we have in our code generator to do the same stuff. You'll still have to sample the problem, so you'll still have to send it to our Leap API, but you don't have to build that model class all on your own. And when I run that, I got a different answer. Remember how we talked about we can have different solutions but maybe the same objective energy? All right, we got one right there. Okay. All right, next. Now that we have and we understand kind of the simple version problem, let's test it and let's iterate on it. All right, so the next sort of steps. Building a prototype, we did that. Next, we'll upgrade. We want to add complexity, test on larger size data, and then kind of iterate through that, update through that. So what we're going to do for the single vehicle routing problem is we're going to stack them on top of each other for multi-vehicle routing. We also have a generator that does that. So we're not going to build that model explicitly. Instead, we're going to use the capacitated vehicle routing generator that D-Wave has in that generator model class. These are the types of inputs. We need to know the demand at the different locations. We need to know how many vehicles are available for us to deliver to those locations. We need to know the capacity of those vehicles. And then we need to know some information about distances, either just the straight distances themselves or locations so we can calculate the distances. The operations that this generator goes through is first processing input. So if we have distances, great. If not, we need to calculate distances. Defining the model inputs as constants, right? That's that bottom level of the directed acyclic graph. Define decision variables also at that bottom level. Then we need to put in all of the route costs. So we kind of put together, okay, these are my routes, use those indexing nodes, add everything together. We'll add constraints here. Remember, we didn't talk about that before, so we'll start adding our capacity constraints. We'll restrict the amount of items that the truck is carrying. And then we'll add the objective. We'll add all the route costs together, put it in our objective function, return the model object. And so the meat of this function is right here, where we're calculating the route costs. Some of this looks a little bit familiar. It might look a little bit more complicated. We're calculating different sorts of route costs for the depot, returning to the depot, to the distribution areas. We're adding our constraint right here, so notice the less than or equal to capacity based off of the demand. And then we're defining our objective here. So this is all in that code base. And then to wrap up, we have to think about, okay, well, what's next for this problem? This is a basic demo available for open source. But what can we do to make it more complicated? What can we do to customize it for a different sort of situation? And so here are some suggestions. First, we can add additional software around what already exists. So maybe we create a better UI. Maybe we think about the information that the client is holding and how we give that information, those routes back to them. So maybe instead of a display that looks like this, we need to create an Excel spreadsheet or a PDF or something. We'll think about maybe additional formulation things. Maybe I need to add some additional complexity into the model to make sense for the situation on the ground. Maybe we have multiple depots. Maybe we have trucks that have different specialties, so we have to kind of define what truck can go to which location based off of what it's carrying. Maybe we have drive time limits. Maybe we have delivery time windows. So these are all sort of extensions to that next level. These are the things we work on in a professional services engagement, taking the basic idea and then translating it into something that's useful for the day-to-day. All right, that was the end of my talk, so thank you for your time.